So we're going to start being able to take the Laplace transform of the unit step function because ultimately what we'd like to do is to solve differential equations related to this unit step function. And so what we can say is that if for some reason we want to take the Laplace transform of a function f at t, and we're just saying it's going to be t minus a times the unit step function of t minus a, that's going to be equal to e to the minus as times the Laplace transform of f at s. All right, so let's go ahead and see how that's going to work out first of all, just verifying this formula. So we know by definition of Laplace transform, we can just go ahead and say this is going to be the limit as c approaches infinity from 0 to c of e to the minus st times the function t minus a times the unit step function t minus a dt. All right, so that's just our definition. And a trick that we can do is we can break this up. So what we could do is we could say, well, this is the integral from 0 to a plus the integral from a to c. All right, so you might remember that from calculus 2 or even calculus 1, where you can just go ahead and say if you have a continuous function, you can break it up at any point a. And so we're going to get this. So we're going to get the integral from 0 to a of e to the minus st function at t minus a, unit step function t minus a, dt, and then plus, now we're going off to infinity. This is a finite integral. And so we're going to say lim as c approaches infinity of the exact same integral, except that's going to go from a to c, e to the minus st f at t minus a. I'm going to have to sneak in the unit step function u of t minus a dt. All right, so now why bother with that? Well, you might remember two things about the unit step function. Anytime that the function ranges from 0, or the value of t ranges from 0 to a, this just goes to 0. You might also remember that anytime the value of t is greater than a, that the value of the unit step function is 1. And so what that means is that this entire integral goes away, and the unit step function at this point just becomes 1. And so what we can do is now we can rewrite the integral very nicely as the limit as c approaches infinity from a to c, e to the minus st, f at t minus a, and technically there's a times 1 here from the unit step function, but I'm not even going to worry about that because it doesn't matter into our equation. And then we have dt. All right, so that's a little bit more manageable to work with, although it looks pretty close to what we had at the beginning, except now there's no unit step function. Now here's the trick to finishing this one off. This is a really cool trick. Let's use a substitution. Let's let v be equal to t minus a. In other words, let's let v be equal to the interior function. Well, that means that v plus a is going to be equal to t. And since we have a function of t, we can take the derivative of both sides. All right, so v is a function of t, so we can just call that dv dt, or just dv. The derivative of a is nothing, and then the derivative of t is dt. Now, the other thing that we can do is we can substitute these bounds back in. All right, so if v is equal to a minus a, so remember this is t equals a and t equals c, all right, well, a minus a is 0. So what that means is that the new integral, which is going to be in terms of v, is going to start at 0. Now, the other good news is that if v is equal to c minus a, and remember c is approaching infinity, well, that's just still going to be infinity because infinity minus any value is still infinity. So this is going to be c. And now we can rewrite this as e to the minus s. We're going to substitute for t. So remember, t is going to be v plus a. And we're going to have f at v dv, right? Since t minus a is v and dt is dv. Right. Now, a really cool trick with this one is that we can distribute the minus s, All right? And that's going to become e to the minus sv times e to the minus sa. And this is just a constant. Okay, so we can factor it to the outside of the original integral. And so we can rewrite this as e to the minus sa lim as c approaches infinity, integral 0 to c e to the minus sv times f at v dv. All right, and what's truly cool about this is that this is just a Laplace transform definition. All right, it's really f at v. All right, so we might have to do a transform of some sort to make that happen, but this one's done at this point, so we can finally rewrite this as e to the minus sa times the Laplace of our function at t after we do some sort of transform on this. All right, so it is a function of t, but we're probably going to need at least one transform to make sure that this does work out to be the Laplace transform. So a pretty cool way of verifying this. Okay, so again, this is just verifying it. And of course, if we really wanted to go back, we could just say that this is e to the minus sa times our function in terms of s, where L of ft is just our function in terms of s. All right, so either way you want to think of it, it still works out to be what we suggested. All right, so in the next video, we're going to take a look at how we can go through and start taking the Laplace transforms of these types of functions that contain the unit step function.